We are discussing thermodynamics, the science related to heat change in physical and chemical changes. In today's lecture, we are going to discuss physical significance of entropy, characteristics of entropy, free energy function, G, work function or Helmholtz function, A, variation of Gibbs free energy with temperature and pressure, and Gibbs-Helmholtz equations. In previous lecture, we discussed entropy changes in reversible and irreversible, that is spontaneous processes, second law of thermodynamics in terms of entropy, entropy change accompanying change of phase, entropy of mixing of ideal gases, and entropy and equilibrium. Now, let us come to physical significance of entropy. Entropy is the measure of unavailable energy of the system. Entropy is represented as unavailable energy divided by temperature taken in Kelvin. Further, entropy is a measure of disorderness or randomness in the system. Increase in entropy means change from an ordered to less ordered, or you can say disordered state. We can also relate entropy and probability. Entropy may be defined as a function of probability of the thermodynamic state. Since we know that both the entropy and thermodynamic probability increase simultaneously in a process, hence the state of equilibrium is the state of maximum probability. Now, let us come to characteristics of entropy. Entropy is an extensive property. It is difficult to determine the absolute value of entropy of a substance, but its value depends on mass of the substance present in the system. Entropy of a system is a state function. It depends on the state variables such as temperature, pressure, volume, and n number of moles, which govern the state of the system. The change in entropy taking place in going from one state to another state does not depend on the path adopted. It actually depends on the final and initial states of the system. Therefore, change in entropy, that is delta S, is equal to entropy in the final state minus entropy in the initial state. The entropy change for a cyclic process is always 0, and the entropy change in the equilibrium state is also equal to 0. So, you can say that for a cyclic process and in equilibrium state, delta S is equal to 0. For natural processes, that is for spontaneous processes, entropy of universe is always increasing, that is delta S of universe is greater than 0 for spontaneous or natural processes. In reversible process, delta S total or delta S universe is always equal to 0, and as you know that delta S universe is equal to delta S system plus delta S surroundings. Therefore, we can say that delta S system is equal to minus delta S surroundings. For adiabatic reversible process, delta S system is equal to delta S surroundings is equal to delta S total, which is equal to 0. In a spontaneous or irreversible process, delta S total or delta S universe is greater than 0. That is, in a spontaneous process, there is always increase in entropy of the universe. To describe spontaneity, we have to discuss some other functions like free energy or work function. There are two thermodynamic quantities that affect reaction spontaneity. First is enthalpy which is represented by H, and second is entropy represented by S. The problem is to put these two quantities together in such a way as to arrive at a single function whose sign will determine whether a reaction is spontaneous or not. This problem was first solved more than a century ago by Willard Gibbs, who introduced a new quantity now called the Gibbs free energy and given the symbol G. Gibbs showed that for a reaction taking place at constant pressure and constant temperature, delta G represents that portion of the total energy change that is available, means free to do useful work. If, for example, delta G for a reaction is minus 300 kilojoules, it is possible to obtain 300 kilojoules of useful work from the reaction. And conversely, if delta G is plus 300 kilojoules, at least that much energy in the form of work must be supplied to make the reaction to take place. Now, let us define Gibbs free energy, the thermodynamic quantity of the system, the decrease in whose value during a process is equal to useful work done by the system is called Gibbs free energy. The free energy function G is mathematically defined as G equal to H minus Ts. Here H is the heat content or enthalpy of the system, T is temperature taken in Kelvin, and S is its entropy. It is single valued function of thermodynamic state of the system and is an extensive property. Now, let us consider a system which undergoes a change of state from first state to second at constant temperature. Here first state is initial state and second state is final state. Then from the equation G equal to H minus Ts, we will have G2 minus G1 equal to H2 minus H1 minus T multiplied by S2 minus S1, or we can say delta G equal to delta H minus T delta S. As you know that delta H is equal to delta E plus P delta V, so we will have delta G equal to delta E plus P delta V minus T delta S. You must recall that delta E is change in internal energy and P delta V is the work done of volume change, that is work of expansion or work of compression. You also know that delta A is equal to delta E minus T delta S, where delta S is change in entropy. Therefore, delta G will come out to be equal to delta A plus P delta V at constant pressure and constant temperature. Here P delta V represents the work done due to expansion against a constant external pressure P. Therefore, it is clear that the decrease in free energy, that is minus delta G, accompanying a process taking place at constant temperature and pressure is equal to the maximum work obtainable from the system other than the work of expansion. This quantity is referred to as the net work, so that net work is equal to W minus P delta V, which is equal to minus delta G. This quantity is of great importance in thermodynamics because the change in free energy is a measure of net work which may be electrical, chemical or surface work. Now we will discuss another function which is known as work function or Helmholtz function. This work function is represented by A and mathematically it is defined as A is equal to E minus Ts. Here E is internal energy of the system and T is temperature taken in Kelvin, and you know that S is the entropy. Since internal energy, temperature and entropy depend upon the thermodynamic state of the system only and not on its previous history, it is evident that the function A is also a single valued function of the state of the system. Now consider an isothermal change at temperature T from the initial state indicated by subscript 1 to the final state indicated by subscript 2. So that A1 equal to E1 minus Ts1, and we are representing this equation by equation number 1, as we will use this equation in further derivations. And in final state A2 is equal to E2 minus Ts2, and this is represented as equation number 2. Now we will subtract equation number 1 from equation number 2 and we will have A2 minus A1 equal to E2 minus E1 minus T, that is temperature, multiplied by S2 minus S1. Now we will have delta A is equal to delta E minus T delta S. This is equation number 3. Here delta A is the change in work function A, delta E is the corresponding change in internal energy, and delta S is the change in entropy of the system. As you know that delta S, that is change in entropy, is equal to Q reversible divided by T, where Q reversible is the heat taken up when the change is carried out in a reversible manner and at constant temperature. So, we have delta A is equal to delta E minus Q reversible. This we have given equation number 4. According to first law of thermodynamics, you know that dE is equal to Q reversible plus W reversible. On rearranging this equation, we will have W reversible equal to delta E minus Q reversible. Now substituting this value in equation number 4, we will get minus delta A equal to minus W reversible. That is, decrease in the work function A in any process at constant temperature gives the maximum work that can be obtained from the system during any change. Theoretically, we have discussed Gibbs free energy. Now we will discuss the variation of Gibbs free energy with temperature and pressure. By definition, you know that mathematically Gibbs free energy is given as G is equal to H minus Ts, and H is equal to E plus PV. Here H is enthalpy. Therefore, G will be equal to E plus PV minus Ts. On differentiating, we will get dG equal to dE plus PdV plus VdP minus TdS minus SdT. This is equation number 5. For an infinitesimal change of a reversible process, you know that dq is equal to dE minus dW. This is the statement of first law of thermodynamics. And you also know that ds is equal to dq divided by T. If the work done is restricted to work of expansion, then dq is equal to dE plus PdV and TdS is equal to dE plus PdV. This is equation number 6. Now comparing equation number 5 and equation number 6, we will have dG equal to dE plus PdV plus VdP minus dE minus PdV minus SdT, or you can say that dG is equal to VdP minus SdT. If pressure remains constant, then dP will be equal to 0 and we will have dG at constant pressure equal to minus SdT again at constant pressure. Or we can say that dG upon dt at constant pressure is equal to minus S. This is equation number 7. But at constant temperature, dt is equal to 0 and we have dG at constant temperature equal to VdP. Rearranging, we will have dG divided by dP at constant temperature equal to V. This is our equation number 8. You have equation number 7 as dG divided by dt at constant pressure equal to minus S, and also on equation number 8 dG by dP at constant temperature equal to V. Now these equations 7 and 8 give the variation of free energy with temperature and pressure respectively. For isothermal process, equation number 8 reduces to dG equal to VdP. Integrating within the limits G1 and G2 and P1 and P2, we will get delta G equal to G2 minus G1 equal to integration of VdP within the limits P1 and P2. For n moles of the gas, you know that PV is equal to nRT, or we can say V is equal to nRT divided by P. On substituting in equation delta G equal to G2 minus G1 equal to integral of V dP within the limits P1 and P2, we will get delta G equal to nRT natural log P2 divided by P1. This is our equation number 9. For isothermal process, we also know that P1 V1 equal to P2 V2. On rearranging, we will have P2 divided by P1 equal to V1 divided by V2. From equation 9, we will get delta G equal to nRT natural log V1 upon V2, and this is equation number 10. From equation 10, we will get delta G equal to nRT natural log V1 upon V2, and changing to base 10 logarithm, we will have delta G equal to 2.303 nRT log of base 10 P2 upon P1, or delta G is equal to 2.303 nRT log of base 10 V1 divided by V2. With the help of these two equations, we can calculate the change in free energy in isothermal process having an ideal gas. To understand the applications of these two equations, let us discuss a mathematical problem. 4 moles of an ideal gas expand isothermally from 1 liter to 10 liters at 300 Kelvin. Calculate the change in free energy of the gas. The value of R, that is gas constant, is given to be equal to 8.314 joules per Kelvin per mole. Now you know that for an isothermal process, delta G is equal to 2.303 nRT log of base 10 V1 upon V2. From the problem, we can have the values for all the variables. V1 is equal to 1 liters, V2 is equal to 10 liters, number of moles is equal to 4, temperature in Kelvin is equal to 300 Kelvin, and R is equal to 8.314 joules per Kelvin per mole. Now substituting these values in the equation, we will get delta G equal to 2.303 multiplied by 300 multiplied by 4 multiplied by 8.314 log of base 10 1 divided by 10. As you know that log of 1 upon 10 will be equal to minus 1, hence we will have the value of delta G equal to 22976.5 multiplied by minus 1, or it is equal to minus 22976.5 joules, or we can say that minus 22.9765 kilojoules. Now we will discuss another problem which will relate delta G to pressure. 2 moles of an ideal gas are allowed to expand reversibly and isothermally at 300 Kelvin from a pressure of 1 atmosphere to a pressure of 0.1 atmosphere. What is the change in Gibbs free energy? Now we will solve this problem by using the relationship of delta G and pressures. The relationship is delta G is equal to 2.303 nRT log of base 10 P2 upon P1. Here P1 is equal to 1 atmosphere, P2 equal to 0.1 atmosphere, temperature in Kelvin is equal to 300 kelvins, R you know that it is equal to 8.314 joules per Kelvin per mole, and number of moles is equal to 2. On substituting these values in the equation, we will get delta G equal to minus 11.4882 kilojoules. Up to now, you have become familiar with the calculations of delta G and delta A, that is Gibbs free energy and Helmholtz function. Now we will relate delta G and delta A to delta H and delta E with the help of Gibbs-Helmholtz equations. These are two equations derived by J.W. Gibbs and H. von Helmholtz. One equation can be expressed in terms of changes in free energy delta G and enthalpy, while the other can be expressed in terms of changes in internal energy delta E and work function delta A. The equation with delta G and delta H is generally employed and is applicable to all processes, chemical or physical, but in a closed system. Now we will derive Gibbs-Helmholtz equation in terms of free energy and enthalpy. You know that dG is equal to V dP minus S dt. At constant pressure, dP will come out to be 0, hence dG will be equal to minus S dt. Let G1 be the initial free energy at temperature T and G1 plus dG1 be the free energy at temperature T plus dt. Then dG1 will be equal to minus S1 dt. This is our equation number 11. Here S1 is the entropy of the system in the initial state. Now suppose the free energy of the system in the final state is G2 at temperature T and G2 plus dG2 is the free energy at temperature T plus dt in the final state. Therefore, we will have dG2 equal to minus S2 dt. This is represented by equation number 12. Here S2 is the entropy of the system in the final state. Now subtracting equation number 11 from equation number 12, we will get dG2 minus dG1 equal to minus S2 minus S1 multiplied by dt. Therefore, d delta G will be equal to minus delta S dt. At constant pressure, d delta G by dt at constant pressure is equal to minus delta S. This is equation number 13. We know that delta G is equal to delta H minus T delta S. Therefore, we will have minus delta S is equal to delta G minus delta H divided by T. This is equation number 14. Now comparing equations 13 and 14, we will have delta G minus delta H divided by T is equal to d delta G divided by dt at constant pressure. Now rearranging, we will have delta G equal to delta H plus T d delta G by dt at constant pressure. This equation is called Helmholtz equation in terms of free energy and enthalpy change at constant pressure. Now we will derive another Gibbs-Helmholtz equation in terms of internal energy and work function. By definition, you know that work function is given as E minus Ts, or we can say delta A is equal to delta E minus T delta S. This is equation number 15, or we will have minus delta S is equal to delta A minus delta E divided by T. This is equation number 16. Now differentiating equation 15, we will get dA equal to dE minus TdS minus S dt. We are giving this equation the number 17. From the first law of thermodynamics, you know that dQ is equal to dE plus P dV, and at constant volume dV is equal to 0, hence dQ will be equal to dE. For a reversible change, ds is equal to dQ divided by T, or dQ is equal to TdS. This is equation number 18. Now comparing the equations 17 and 18, we will get dA equal to minus S dt. Let A1 be the work function in its initial state at temperature T and A1 plus dA1 be the work function in its initial state at T plus dt, and A2 be the work function in its final state at temperature T and A2 plus dA2 be the work function in its final state at T plus dt. Then dA1 will be equal to minus S1 dt. This is equation number 19, and dA2 will be equal to minus S2 dt, which is equation number 20. Now S1 and S2 are the entropies of the system in initial and final states of the system respectively. Subtracting equation number 19 from equation number 20, we will get dA2 minus dA1, which is equal to minus S2 minus S1 into dt. Or we can say d delta A is equal to minus delta S dt at constant volume. Now we will have d delta A by dt at constant volume equal to minus delta S. From equation 16, we will have delta A minus delta E divided by T equal to minus delta S, and on comparison, we will have delta A minus delta E divided by T equal to d delta A by dt at constant volume. On rearranging, we will have delta A equal to delta E plus T d delta A by dt at constant volume. This equation is called Gibbs-Helmholtz equation in terms of internal energy and work function at constant volume. As you have derived Gibbs-Helmholtz equations, now you can apply these equations in mathematical calculations. Now we will revise what we have discussed today. In this lecture, we learnt about physical significance of entropy, characteristics of entropy, free energy function, work function or Helmholtz function, variation of Gibbs free energy with temperature and pressure, and derivations of Gibbs-Helmholtz equations in terms of free energy and enthalpy, and also in terms of internal energy and work function. In next lecture, we will apply these Gibbs-Helmholtz equations